Welcome to Embedded. I'm Alicia White alongside Christopher White. This week we will be speaking with Jean Labrosse, author of the MicroCOS real-time operating system.
Hi, Sean. Thanks for joining us today.
Hello. How you doing?
Could you tell us about yourself?
Well, I have a master's degree in electrical engineering, and I fell in love with microprocessors just about the time they came out, circa Intel 8080 and 68000 from Motorola. I've been doing embedded systems for almost 40 years, and I founded Micrium in 1999, and Micrium was actually acquired recently by a company called Silicon Labs in Austin, Texas.
I have some questions about that, but I have a lot more questions about the real-time operating system and learning how to deal with it and Micrium and MicroCOS. But before we do that, we have strange lightning round questions where we ask you questions and want short answers. Sort of a getting to know you thing.
You bet.
Christopher, you're first.
Okay, 8 or 32-bit?
32.
What language should be taught first in university courses?
English.
Sorry, what programming language?
Oh, well, I mean, you need English to program any programming language, but I would probably say C.
Little or big endian?
For communications, I would say big endian, but little endian is the norm.
That's the correct answer.
Least favorite electrical component?
Electrical component, least favorable.
These are, I mean, they're short, but they're tough.
Inductor.
Oh, I agree with that. Favorite fictional robot?
C3PO.
Oh, see, this is great.
This is great. This is going to be fine. Favorite processor of all time?
Actually, I like the 68HC11 processor because it was simpler, but nowadays probably the Cortex-M is my favorite. Not because of the architecture of the instruction set, but mostly because of its built-in debugging capabilities. And
the fact that it's everywhere.
Yeah, fortunately or unfortunately.
It's all we work on now, Cortex-Ms. What science fiction technology or concept do you think will become real in our lifetimes?
Well, unfortunately, self-driving cars is going to happen, very quickly. So that was my favorite technology concept that I always thought would be really cool to see. We saw that in some movies in the past, and I was always quite impressed with that. So self-driving cars. And
I agree. We're definitely going to see that one, and soon, I think.
Yeah.
So from Andre, he asks, what is your favorite Gino Vanelli song?
Okay, Gino Vanelli. I don't know how many people know Gino Vanelli, but he's a very awesome musician. He's created over 200 songs, and if I had to select one, I'd say Brother to Brother.
All right. I think that will do, unless you have any more, Christopher. Oh, here's one. Is a cell phone an embedded system?
Years ago, I'd say it was an embedded system, but nowadays I would think it's more of a general purpose computer.
Fair enough. What is a workday like for you?
Oh, that's kind of complicated. It's split between two things, writing and answering emails, getting into meetings, and then I work at night, and that's when I actually do the real work.
What is the real work?
Well, I mean, do things that we talked about during the meetings and answering the emails with the questions people ask and things that they want to have done. So if I have some things to do, and most often I do them at night or on the weekends.
We hear this a lot where engineers will say, I spend most of my days in meetings and talking to people. And usually it's not people whose title is engineer. It's people whose title used to be engineer, and now their title is CEO or chief architect. And now they spend their days in meetings and they finally get to work after work.
Yep. That'd be the case.
why isn't the hard part of dealing with people the work? I mean, the coding part's the fun part, right?
Yeah, and I don't do that much coding anymore. I mean, we have people that does that, and that was the fun part. So as you progress in engineering, as you progress and you get promotions, and you, in my case, started a business, you get to do less of that and more of the the management, the project planning, and none of the fun stuff anymore. Others do that.
It's so sad when you have to give away your toys and other people get to write your software for you.
Yeah. It's a difficult thing to let go of, that's for sure.
So you started writing this operating system in the 90s, is that right?
That's correct.
And did you start writing it as part of an article for Embedded Systems program, or did you have it and then write the article?
Well, actually, it all started where I wrote the operating system because I was using an operating system and I found a bug in it. At least my team found a bug in it. And we contacted the manufacturer. Long story short, we were out of our maintenance period, and they didn't want to help us fix the bug that was in their operating system. So I decided, well, how hard could it be to write an operating system? And I decided, let's go ahead and do it.
And that was a time where lots of people decided, hey, let's just write our own operating system. This is not working for us. It used to be super common, but now it's pretty rare. How did the industry finally figure out that that was not a good use of time?
Because, I mean, they pretty much all do the same thing, and it's not a good use of your time to do that. I mean, as embedded systems are getting more and more complex, I think you want to spend more time dealing with the value added to your product instead of spending your time with infrastructure software, which is, real-time kernel and protocol stacks and so on.
This is an argument I have constantly with clients, where it's like, your product is this. Why are you making infrastructure?
Well, I mean, case in point, how many times people have rewritten a UART driver? I mean, something as simple as that.
Thank you. Yes.
Right? So it's exactly the same thing. I mean, although a real-time operating system is a little bit trickier. I mean, when I first started doing it, I thought, well, how hard could it be? It's context switching of registers, no big deal. I could do that. I'm a good programmer. And then after, once I got to version 1.11 or 1.12, I figured out that was not that trivial, because there's some the race conditions you got to really, really be careful with. So it's not that easy. So, and the other thing that's kind of interesting is it really takes between 7 and 10 years to get a product mature, such as a real-time kernel. Mature and accepted in the industry. So anything that comes out new nowadays, it's got some time before it gets to be matured and accepted.
The baking time when all the bugs are found, or when 50% of the bugs are found. The easy 50.
Well, I'd like to think that most of the bugs have been found by now. And it's been 10 plus years.
And those articles in embedded system programming, you wrote them after you wrote the operating system, but they were only a few pages. I mean, it was 3 parts and like 5 pages each.
Yeah, it was something like that. What happened is I actually wrote the kernel, and then I contacted the Embedded Systems Programming magazine to have it published. And at the time when I wrote the article, it was actually 70 pages. So Embedded Systems Programming says, well, we can't publish a book like that. We can't publish that. So they actually broke it down into 3 parts of 5 or 6 pages each, May, June 1992, and September, I believe, 1992. So then afterwards, a different publisher contacted me and said, hey, by the way, those 70 pages that you've sent us a while back to get published in a magazine. Would you be interested in write a book? And I said, sure. If why not? And I said, well, if I'm going to write a book, I might as well make it a real book, not a booklet. 70 pages to me was kind of tiny, so I decided to go ahead and write the book. And I think it was early March, April, May, or something like that, 1993, that the book actually got published.
And it was longer than 70 pages, but you went over all of the how an RTOS should work, and you used yours as an example.
Pretty much, yeah. I explained the concepts, what's a semaphore, what's a mailbox, and how this context switch works. And, you had, at least at the time, there were some books out there explaining about operating systems in general terms, the Tannenbaum book, for example. And there was really no actual code that you could get that you could actually try it on the processor. And the first processor I tried it on was a 68HC11 processor. So very easy to use on a 8-bit processor like that. And in fact, it's kind of a misconception that people think that real-time kernels are only used on 32-bit processors. I mean, they kind of started on 8 bits, actually.
Yeah, these kids and their 32-bit processors.
Exactly.
So you were working probably a full-time job. You were making your own operating system, and you were writing a book.
Yep.
After you finished the book, how many years did it take before you were willing to even consider writing another?
I went from 1992 to 1998. So the MicroCOS 2, it actually took a while before the book got sold. So it took something like 4 or 5 years before we saw any revenue, because they were giving me royalties. I mean, I say us, my wife and I, because she gets the royalties. That was meant as a joke, by the way.
Sorry.
So anyway, it took a while for the royalties to start kicking in. In fact, what they did is they gave me an advance, and then the advance took a long time before it got depleted. So anyway, I really never did it for the money. I really did it for the righteousness of thing. I wanted to, teach others, and especially, when I found the bug in the operating system that we were using commercially, it was kind of like upsetting to see that. So I decided, well, I'm going to write an operating system, and I'm going to provide all the source code to it instead of, a bunch of binary files. So that was the difference. It really was not for the money. It was really more for the helping the industry. And then I started doing lectures at conferences in 1993. Same purpose there. It was not. I was not looking for fame or glory or anything like that. It was just like, what can I do to help so that others don't get into that situation?
And how did you go from that to making it so that there was Micrium and you had a way to support and sell the operating system in addition to teaching about it?
Well, that was also kind of an accident. In the 1995, 1996 timeframe, a gentleman by the name of Mike Kaskowitz, who was working at a company called VLSI Technologies, contacted me, and he basically says, "Hey, look, I'm looking to use your real-time kernel MicroCOS for a processor that we're actually saying. For a processor we're actually selling." And then the processor is an ARM6. And I said, what the heck is an ARM6? Oh yeah, very, very popular. It's going to be popular in the years to come. And I'm going like, I've never heard this, about this processor. I heard about the 68,000 that was popular. X186 or X86 processors were quite popular, but ARM6, who the heck would ever want to use those? Nobody heard about them. So anyway, so he actually used the kernel. So he basically said, oh yeah, what I'd like to do is license your software so that I could actually provide that to my customers as an example of multitasking this 32-bit processor. Okay, fine. So I said, well, what's licensing? I had no idea what that was. So I say, yeah, we write a contract and you give me the rights to actually provide that to my customers, and I write you a check between anywhere between $5,000 and $10,000. And I said, well, $10,000 sounds great. So let's go ahead and do it. So a few weeks later, got the contract and I got the check in the mail, and it was downhill from there. I mean, once I had that, I opened up a little BBS at home, and I put my contact information in the book. Actually, it was in the book all along in 1993. So people started contacting me. That's how he got a hold of me. And oddly enough, I mean, other companies contacted me well afterwards. HP, for example, contacted me. I don't know, Kodak, a whole bunch of companies afterwards. And I said, hey, I know about this licensing concept, and if you want to use it, this is what we'll do.
Before that, it hadn't been licensed. I mean, it had been out there and free for people to use, although. Correct. Maybe you would have gotten annoyed if people were using and selling it.
Right, and that was the concept. I mean, the concept was all along was always, if you're going to use it in a commercial application, I think you should do the right thing and share the wealth. But if you're going to use it for non-commercial use for a hobbyist, then absolutely go ahead and use it. I'd be more than happy that you learn about real-time kernels as well as use it for your own projects at home. So, but initially, I mean, I was kind of this naive engineer, do the right thing, write software, very clean code. And that was one of the things I wanted to promote also. I've always been a nag about clean code, very well organized, lining up equal signs, lining up comment signs, /* and / or vice versa. And, I've always been very, very picky about, putting proper comments. So it's kind of selfish in a way that I wanted to have that way of writing code out there, as well as, here's an operating system you could play with and you could learn about.
So when you were developing this at first and exploring how to distribute it and how you wanted people to use it, this was about the same time that Linux was kind of just beginning to enter people's consciousness, and the same thing,
right.
GNU as a license. Was that kind of on your radar? Were you thinking about those things, or was this just kind of everything was so new that it wasn't really clear?
It was new, and anything you learned about, I mean, the internet, I mean, the websites and stuff, that's not that old. I mean, it's not something that was in existence in the 95, 96 time frame and stuff. So all the information you read about was pretty much magazines. So, and I wasn't really keen on Linux at the time, or I really didn't get involved in any of that. So to me, it was like completely different things. So, I mean, in a way, you could say that I kind of started this whole open source on the embedded side of things. Not Linux was a little bit higher end systems. I mean, you look today, you have free RTOS that's out there. You have lightweight IP for protocol stack. So there's a whole bunch of stuff that came out afterwards. And oh, by the way, when I came out with the article, there's a lot of real-time kernel or real-time operating system, however you want to call them, companies that were quite upset about the article, and they were actually threatening Tyler Sperry, who was the editor at the time, bad things, because how dare you put a real-time kernel as an article in the magazine? How dare you expose this secret of ours that we've been charging a fortune for? So it was kind of interesting. In fact, I mean, oddly enough, the reason, like I said earlier, the reason I actually came out with the real-time kernels was because we found bugs in the operating system, and it all started when I started with one operating system that was kind of cheap, but we could never get it to work. So we got this real-time kernel from a company called Microdigital in California, and we were contacted them by phone. At the time, there was no email or internet. We were contacting them by phone and saying, look, we can't get this to work. Could you please tell us what we need to do and stuff. And anyway, after spending like a month or so, we couldn't get it to work. So then we switched to Vertex, and Vertex was like $5,000 at the time, so quite expensive for a company way back in the 89 timeframe, 88 timeframe. So we decided, let's go ahead and spend the money, spend the $5,000, and 90 days later, your maintenance expired, and that's about the time we actually found the bug. And they told us, well, sorry, we can't help you. Your maintenance expired, and unless you pay us back again, we won't fix the bug.
That's extortion.
Yeah, so I mean, so part of that whole story is more of the righteousness of things, and this was not fair. I didn't think it was fair. Look, and specifically, the second operating system was Ready Systems Vertex, which at the time was very popular and was known to be bug free. In fact, for years they were giving a Volkswagen bug if somebody found the bug in their software. So I didn't claim the bug. I didn't really like that car anyway, but so I didn't go any further with that. But anyway, so we found the bug. We pinpointed the bug, and it took them a whole year from the time we found it to the time they fixed it. So that's when I decided to actually write that. So
a reminder to everyone about how difficult things were before the internet, before communication was easy, before people, if you've got a security bug now and talk to Microsoft and they said, pay me, the outrage would be through the roof.
Exactly. Well, and it's funny because I think that the complexity is just as complex today as it was back then, oddly enough. Today, you have high-end processors, you get better tools, you get debuggers, you get all kinds of profiling tools, you get a MISRA, you get static analysis. So you get a lot of these tools that you didn't have back then, and all these tools that you have, they're great, but the complexity of the software, the expectation from customers has gone up tremendously. So and back then we used to have 8 kilobytes of code space, 256 512 bytes of RAM, no debuggers. There's no flash. You got to erase EPROMs. Just the tools were just archaic as could be, but the applications were super simple. So applications were simple. It was difficult to debug. You actually had to stare at your code a lot more than people do nowadays. People just go ahead and write code and we'll figure that out, when we actually test it or in the debug stage. Back then, you can't wait 30 minutes for the EPROM to erase. You have to have a whole stack of EPROMs in a tray, being erased while you're actually looking at your code. So there was more staring down is more design back then, I thought, than there is today.
Well, yes, because you had so much time between when you could try out a solution. And so now we've talked about this on the show. Sometimes you end up sort of banging on your keyboard like a monkey trying all the options because you can. But if all of the options took 30 minutes each, right, you would have to think it through. And that often makes for better software. It's just to stop just trying all the options and to think, what am I doing and how do I get from here to there?
Yeah, and there's that old adage, I guess it's a word, is adage, don't just sit there, do something. I'd rather it be just don't do something, sit there.
Yeah.
You got to think about it a little bit longer before you do things. And it's acceptable nowadays that people actually write code, throw it away, and then write the right code afterwards. I've heard some people say, it's okay to write throwaway code in the beginning because you'll do that regardless. I don't believe that.
Okay, we've thrown around a lot of RTOS terms without defining any of them. Maybe we should come to the point where we actually define some stuff.
Sure.
Starting with RTOS.
All right, what is it, right?
Yes.
An RTOS is also what we call a real-time kernel. Our RTOS means real-time operating system, and a real-time kernel is really Okay, so an RTOS is really not an operating system per se. It's the multitasking side of an operating system. So typically, an RTOS is software that manages the time of a CPU, and each of the application that each so the application is divided in subcomponents called task, and each task is responsible for a portion of the application that you're doing. Each task is given a priority that you based on the importance of the task, and then each task typically is an infinite loop that waits for an event to occur. When the event occurs, the RTOS or the kernel will schedule the task to execute, and it will actually run that task on the single CPU that you have. Let's say it's assuming a single CPU.
I have sometimes used the analogy of a nursery school teacher, that if you are running on a CPU and you're going bare metal, it's sort of like you're a kid who is doing like one thing at a time, and that's okay. But as soon as you have 6 kids, you start needing a teacher to organize who gets to go to the bathroom when, and who gets to play with the red crown, and who gets to pet the gerbil. And so you have to have some organization, and the RTOS is that nursery school teacher that provides the organization and says who gets to do what, who has access to what tools, and what features. Is that a terrible analogy, or is that just funny?
It's both.
Rating your own jokes.
No. It's not a terrible analogy. It's a good one. I mean, the whole idea is that you have a single CPU. You have an RTOS is a way to orchestrate things to be done in a sequence based on priorities. Not everything is important in your day-to-day work, and it's the same thing as a manager. You basically have to figure out what's more important. What do you have to do first? What do you have to do next? And the RTOS just makes that easy. Unfortunately, when we work, when we take phone calls, when we are in meetings and stuff, we don't have this piece of software that kind of brings us back to say, oh, by the way, is this really important? Do we need to do this right now? And that's what the RTOS does. It says, okay, an event occurs, something happens. The scheduler says, the real-time operating system, is this the most important thing that we need to do? If the answer is yes, then we do it. If not, then we keep on continuing what we were doing before. And it so happens that if there's nothing else left to do, then the RTOS runs what's called the idle task, and that's a perfect place where we could actually put the processor to sleep, because when the CPU has nothing else to do task-wise, we could actually go in low-power mode on most of the modern CPUs, and thus reduce power consumption and save on batteries.
So what distinguishes an RTOS from just a simple scheduler that you base on a timer?
Well, the basic scheduler that you would base on a timer would typically be implementing a state machine where somehow events would set flags, and then you would execute those events by looking at the flags, but it'd typically be implemented as a polling loop. So you'd actually check to see if any of these flags were set, and if the flag was set, you actually execute the code for that. So it's not as orchestrated as if you had an RTOS, because it's all built in. There's one more thing that you need to have for an RTOS, and that is each task has to have its own stack, and thus each task thinks it has the CPU all to itself, because whenever a task executes and something else of higher importance occurs, then the CPU registers of that task are saved on the task stack, and then the new CPU registers of the new task, the more important task, gets loaded into the CPU, and then that task executes. So all that orchestration is done all behind the scenes, and it's done as efficiently as we possibly can. People designing real-time operating systems spend their time figuring out how to save just about every clock cycle to do what needs to be done and as quickly as possible. So that most of the time is not spent in the operating system, it's spent doing the work that the operating system is supposed to do.
Okay, so that's how the scheduler works, and switches between tasks and then goes to idle. Most operating systems today operate that way. What's the real-time part of the
latency?
Latency, determinism, preemptive scheduling. A preemptive scheduler is, and that's the case for most real-time kernels or real-time operating systems. Preemptive means that whenever there's a more important thing that has to happen, then it will actually preempt or stop what you were doing before and switch over to the more important task. So preemptive scheduling is very, very critical for an RTOS. In fact, if you remember the days of Windows 3.1, Windows 3.1 was not a real-time scheduler. So for example, you had an interrupt. The interrupt service routine made a more important task ready to run. But what happened was the interrupt returned to the interrupted task. The current task was ready to relinquish the CPU, was the operating system invoked and gave the control of the CPU to the high priority task that was just made ready to run by that ISR. So there could have been a long delay. In fact, I remember that Windows 3.1 used to hang a lot if the task that you were running was sent on a tailspin. So not the most efficient thing. I don't know of any real-time operating system nowadays that don't have preemptive scheduling.
I mean, it makes a lot of sense. The priority inversion is the worst part about non-preemptive systems. Is that right?
Well, the priority inversion occurs with preemptive scheduling just the same. And what happens there is that you are a low priority task. You obtain a resource that is shared by a high priority task. So you want the resource, you typically use a mechanism called the semaphore. So you grab the semaphore, which is kind of like a flag that you just grab and you say, I'm going to own this resource until I release the flag. So you grab the resource, you grab the flag, you access the resource, and during that time, let's say a more important task occurs, the event that a more important task was waiting for just occurred, and it so happens that the RTOS will switch to that task, of course, because it's the most important one. The RTOS will actually, the more important task that says, oh, I would like to have access to that resource, but you can't have access to that resource. It's already owned by the low priority task. So that high priority task gets to be suspended, waiting on that resource to be relinquished by the lower priority task. So what happens there is that you can have medium priority tasks that occurs in between, because medium priorities are more important than low priority ones, of course. It's a preemptive scheduler. It does its job. So you're delaying the access to the resource by the high priority task, the more medium priority task that you have. So anyway, so long story short, that's the priority inversion. A low priority task is acting as if it was more important than a more important task. So there are mechanisms in most RTOSs nowadays. It's called mutual exclusion semaphores. And those mutual exclusion semaphores, what they do is they actually raise the priority of that low priority task to be the same as the priority of the high priority task, so that it could hurry up and relinquish the resource as quickly as possible. And then once it relinquishes the resource, the priority of that task gets lowered back to where it was, and now the high priority task could have access to that resource.
And if you're out there like trying to follow along without a whiteboard and maybe driving at the same time, imagine that your debug task has a hold of your UART, and some other task, some communication important task comes along and needs the UART, like really needs it. Well, it has to wait for the stupid debugging to finish. And then the debugging gets interrupted by like the USB that comes, and now your really high priority command task has to wait for the stupid USB thing and the debug thing, unless you have this mutex which says the debug has to finish so that the high priority command handling can happen.
It sounds like you've written a lot of software, because you actually put explicatives to tasks and stuff like anybody that's written a lot of code will call things stupid this and stupid that. So you've been around the bush.
So when isn't it a good time to use an RTOS? I know that you write about RTOSs and you care about them and you sell them.
You're in the pocket of big RTOS.
You are totally in the pocket of big RTOS. When should I not consider that? When should I say, no, I have a thing. I don't need to worry about it quite yet?
Well, if you have a very, very simple application and you could do it with a super loop and you don't have complex communication protocols, you don't have TCP/IP, you don't have USB stacks, you don't have file systems, you don't have a lot of these things. Your application is very, very simple. It fits within a few kilobytes of code space. And then the responsiveness of a super loop or a while one loop would be sufficient to handle your product. Then I think you don't need one. It starts to get complicated as soon as you start adding protocol stacks, TCP/IP, like I said, file system. Oh my God, a GUI. If you want to put a GUI on there and you're single threaded, just imagine you're painting a screen with hundreds of pixels, and then your control loop will have to suffer because by the time you paint, for example, 320 what is it? What's the resolution? Quarter VGA 320 by
240, like
240. That's like 76 kilobytes worth of pixels that you would have to paint. Imagine updating a display with that many pixels. If you're also doing a control loop in your super loop, there's a good likelihood you'll miss your deadlines.
Yeah. So GUIs and all of the communication protocols. BLE was one I kept thinking, oh, no, it's simple enough. But no, you really do need an operating system for that, sadly.
Yeah. I would say anytime you start adding complex protocols, especially those protocols that you purchase off the shelf or you get from somewhere, because you don't have any control over how they actually operate. So a real-time kernel will actually say, doesn't matter if I don't know how it operates, I'm going to give it a lower priority task than my control loop. And when my control loop needs to run, it will always be guaranteed to run, irrespective of what my protocol stacks are doing. So clearly, in that case, that would make a lot of sense.
So MicroCOS runs on many different processors.
Name it, it runs on it.
And having ported software from one processor to another a few times, that's not always the most easy or fun thing to do. When did you decide to commit to, yes, I'm going to run on everything?
Well, actually, the porting process is the easy thing. The hard thing is understanding the new CPU architecture, understanding the tools, getting the eval board, getting to know the debug environment and all that. So, I mean, that's the hard part. Once you understand all that, porting it is really trivial because all you need to do is you need to set up a timer interrupt for what's called time delays and timeouts. So the tick rate, for example, that's what it's called. And then the other thing is you need to figure out how do you actually save all the CPU registers on one stack and then restores them from another stack. And that's pretty much the extent of a port. So, the writing of the port is the easy thing. So, how do you decide whether you need to do it or not? In my case, I mean, if I had a customer that was willing to send me a check, like I had mentioned before, then I would certainly be motivated to do the port and provide that work. But over the years, I mean, different customers, and then since we started Micrium, over the years. We have all kinds of customers asking us to port on Power PCs and on ARM Cortex-M, Cortex-A, Cortex-R, Renesas RX. I mean, name a processor. So, of course, we're motivated by doing it from a commercial point of view.
What about the compilers? I mean, we should have had that as a lightning round question. What's your least favorite compiler? You don't have to answer. It's okay.
Well, anything that's non-reentrant. I don't think anybody has a non-reentrant compiler anymore. But I mean, there's not that many choices nowadays, right? I mean, there's GNU, there's IAR, there's Kyle, and what else?
What is non-reentrant for compilers? I know what it would be for a task.
Yeah, non-reentrant means that if you're starting, and that's the thing, it's typically used for multitasking. That's really an issue with multitasking. So non-reentrant really means that if I'm starting, for example, strtok, the standard library function where you're actually parsing an ASCII string for delimiters. So what happens that every time you invoke that function, it stores inside of a global variable that it keeps the current location of where it's actually found a token, the last token. And it replaces that location with a null pointer, and then it moves to the next location. So next time you reinvoke string tok, then it actually parses the remaining of that string. So just imagine if you were to call that function by two separate tasks that could actually execute at any given point. The first task, is expecting to have that pointing to one token, and then the other task is pointing to a different location, a different string. So that's the non-reentrancy of things.
So that makes sense. That was sort of what I was expecting. And so when you say a compiler is non-reentrant, you mean the library that it's built, the like C library. Okay, that makes more sense.
Yeah, there were some compilers years ago. I can't recall exactly which ones they were, but there were some compilers that were actually designed to be non-reentrant, not just the libraries. They had to make some assumptions about things. I just don't recall who they were.
I can see how you could optimize things so much that having reentrant. Yes, all right, I get it.
Especially for really small devices or something.
Yeah, exactly.
So do you support all the compilers? GNU, IAR, Kyle?
Yep.
Clang.
Clang?
What's that?
That's the new hot open source compiler.
It's sort of like GCC.
It's kind of moving as a replacement for GCC in a lot of cases.
Wow, never heard of it.
You will.
Nobody's
someday.
ever asked. Yeah, probably. Yeah, probably.
It's very nice.
Yeah, cool. It is actually pretty nice.
And that's for ARM platforms?
Yep. And x86 and a bunch of other stuff.
Cool.
So one of the ways that MicroCOS has changed over the years is you got it certifiable for FAA and FDA use. Right. What was that like?
Actually, it was quite easy. I didn't have to do anything. We actually, some gentleman by the name of Scott Nowell at Validated Software at one point was having had a customer that needed to have certification for an operating system, and he magically found my book, and he says, well, I'm going to actually use this because I get all the source code. It's very clean, very well written, well organized. I could actually get this through certification. So they actually did kind of like a reverse engineering, which is allowed by the FAA to do. You take a piece of code, and you go backwards and create requirement docs and stuff, and he was able to create the artifacts for an avionics application where you could actually prove that the software is tested 100%. So they did test suites. So they tested 100% of the code. Everything was verified, all the different paths of the code. And actually, they only had to change some 20 lines or so for it to be certified for this avionics application. Yep.
It would be extremely gratifying to have somebody else do that and say, yeah, you did a good job.
Yeah. No, it's fantastic because, I mean, it gives you a lot of credibility. Look, I mean, if it's certified for avionics use, and it was certified for DO-178B level A, which is the most stringent certification you could get. So, yeah, it was extremely gratifying. And like I said, they only had to change 20 or so lines of code, which was very, very cool.
And so now is it Misra compatible?
So then that's another controversy that I have. I mean, Misra is meant to be for the purpose of writing clean code, to make sure that you don't do any stupid things with stupid tasks, if we could go back to that. But the way I look at Misra is it helps developers to write clean code. That's absolutely true. But if you have your code already certified for avionics or medical applications, the MISRA, even if you violate some MISRA-C rules, your code has been validated in very stringent environments. So, if you don't follow all the MISRA-C rules, then, I got a better way to demonstrate that the code is robust. And that was the whole purpose of MISRA, is to produce robust code. So, to answer your question, yes, we have some MISRA-C documents that explains which of the rules that we follow and which ones we don't, because we don't follow all the MISRA-C rules because some of them just didn't make sense for us. For example, in a real-time kernel, for example, you call an API, and then the API, you pass a pointer, and then you pass some arguments. So one of the things I do in the kernel is actually check to see if each of the arguments are proper. So are you passing a null pointer when you're not supposed to pass a null pointer? Well, if you do pass a null pointer you're not supposed to, the code returns immediately. Well, in MISRA-C, you're not supposed to have an immediate return call like that. You're supposed to have a single return point in your code. Well, to me, it made more sense to say, hey, as soon as I detect the error, I'm going to kick it out, tell the user you did something you're not supposed to do. So there are things like that in the code that just in the MISRA-C rules that didn't make sense, that I decided that we would not be following.
And most people don't follow all of the MISRA-C rules. You choose the ones you want that make sense for your system, and you accept that sometimes it just isn't right for you.
Yeah, actually, I met one of the gentlemen that it was part of the 10 people that's on the committee for the MISRA-C committee, and he told me if ever anybody follows 100% of the rules, because some of them are kind of contradictory, something's wrong with you.
That's true.
Good to know ahead of time.
Well, there are a lot of rules, and they cover different kinds of things. So, and that's why most of the compilers that have static tests for MISRA, they have lots of checkboxes that say, well, I don't care about these rules, but these ones I do, and it's not going to yell at you for some of them. So,
Although passing pointers and functions reminds me that we did get a question from Twitter about hooks, RTOS hooks. What are they, and how do they work?
Sounds painful.
Nah, it doesn't hurt at all. So an RTOS hook is a callback function that is actually invoked, for example, in the idle task. Whenever the kernel doesn't have anything else to do, it's an infinite loop. So like I said before, you could actually put the processor to sleep when there's nothing else to do, because all the events that all the tasks are waiting for have not occurred. So the processor spins around doing nothing. So in that case, in the microCOS kernel, for example, there's a function call that I call that's called OS hook or something, OS idle task hook or something. And that's where you would actually put the code to put the processor to sleep in whatever sleep mode you want to use for that case. For example, whenever there's a context switch, whenever we're saving registers for one task and restoring the registers for another task, there's another hook function or a callback. So it used to be called hook, now it's called a callback. So the context switch hook could be done or could be used to save things. For example, I want to save floating point registers, or I want to save MPU registers on a context switch. Things that you'd want to do for example, you want to turn on an output port as soon as you're starting the context switch, and you want to turn it off, when you're done or something, to show how long the context switch code takes to execute or something. So there's a lot of stuff you could do with these hook functions. There's one for the timer, there's one for the tick hook. So there's all these different things that are available in the kernel.
So you can extend and modify the behavior of the kernel
without having to change the base kernel itself, correct? I don't want customers to go in and change the kernel, even though we provide it all in source form. We don't want them to go in and change the kernel. That's why we give them callbacks that they could actually change, and they don't have to go in the actual source code of the kernel and say, I'll change this, I'll change that.
Well, the context switching one is really useful, because I have done what you've said, although not to measure context switching, but for each when I enter a task, I turn on this GPIO. When I leave it, I turn it off. And when I enter a different task, I turn on that GPIO. And when I leave, I turn it off. And then the scope can show me exactly where I'm spending all of my times and tasks. And when I'm going to sleep, everybody needs to turn themselves off the right way, go into the lowest power state. And so when you get to the idle mode, that's what you do.
Absolutely. And in fact, there are some tools that you could actually get. There's a tool called System View from Seger that recently, it just came out, actually. And then it actually does exactly that, but on a really, really cool Windows-based environment. In fact, it works with Macs and Linux and all that. But it's really cool because it gives you a timeline of all your different tasks on a horizontal timeline. And you could see how long each task executed, the ISRs, when the task was ready to run. So all of that is pretty neat, is all displayed graphically. And it requires just a little bit of instrumentation, not any different pretty much than what you've done with your I/O port. So there's some very, very slick tools that you could use nowadays to do exactly what you were doing from that.
For all that we started out with no breakpoints and flashing EPROMs to getting 2 breakpoints and being grateful for them, our tools are getting better.
Absolutely. Absolutely. Well, the other thing, the problem is, okay, so breakpoints are great. It's really nice to have that capability, but it's not good for everything. It's good for testing algorithms, but for real-time applications, there's a lot of cases where you just cannot stop the application to monitor what's going on. So, for example, you're mixing chemicals. You can't say, "Oh, when I get to this point, stop." And the chemicals will still keep mixing, but the results you'll get from the mixing will have been far gone away once you start executing again. When you're running engine control, for example, you're firing spark plugs on an engine. You just can't say, "Oh, let's hit a breakpoint." Whatever you're connected to will potentially get damage. You're flying an airplane. You can't say, well, let's put a breakpoint when we're, banking left or banking right just to see what the result will be. Your control system will go dead. So and most likely the passengers will also follow suit with that. So there's a lot of applications that, unfortunately, everybody does the same thing. They blink LEDs. They have a little GUI interface. They actually display numbers. They do printf statements. The infamous printf statements. So, oddly enough, at Micrium, we have this really cool tool that's called uCProbe that allows you to see at runtime the value of variables, and the same thing. And in fact, we're able to display variables such as kernel awareness variable. So we show you how many tasks you have, how many and the amount of stack space each task is consuming, the CPU usage on a per task basis. So there's a lot of information we're able to display at runtime without interfering with the CPU, and that's in a lot of cases, a very important behavior that a very important tool that you have, because how would you do it otherwise? If you're adding printf statements, you're adding artifacts to your code, and thus changing the behavior. So what you're seeing is not really necessarily what's going to be when you remove those printf statements.
And that's why your code doesn't work when you don't debug.
Exactly. Exactly. Well, and another thing that's the number one issue that I get all the time, that our support guys get all the time, is stack overflows. I actually wrote a blog on our website. You could check our website. I wrote a 2-part blog on stack checking and stack overflows. And that is, there is no easy way really to see how much stack space your task is using unless you actually monitor that at runtime. So what a lot of people do is they oversize their stacks because they say, well, this idle task, for example, you don't want to put 4 kilobytes of stack space for an idle task because you just don't need that much. You're going to be wasting RAM that other tasks could be using. So by knowing how much stack space you're actually using, is extremely beneficial. But a lot of times what happens is you undersize your stack overflows. And by overflowing, I mean you're writing over some values somewhere in memory that you're not supposed to, because you've pushed your elements on the stack a little bit too far, and you get some weird behaviors. So, anytime somebody calls us up and says, "Oh, by the way, I've been running the application, been running great. I love your operating system, blah, blah, blah. But after a few hours, I got weird things happening." Well, how big is your stack? Do you have enough stack space? Well, I don't know. How big should they be? Or how do I know if I have enough stack space? Well, you need a tool to do that.
All right. So I want to go on from there and ask about open source RTOSs.
Okay.
So there are some open source ones that are getting better. RTEMS and free RTOS are both the ones that I keep looking at and thinking, that looks pretty good. Have you dealt with the competition? Do you look at it? Do you just not worry about it?
Well, oddly enough, the free is always our biggest competition. I mean, Micrium sells real-time operating system, real-time kernels. They're not cheap, I would say, but at the same time, your time is not cheap, or the developer's time is not cheap. So I look at, and so our number one competitor, bar none, is free. Free operating systems. So we always compete against that. But it's the same thing as if I were to give you a free puppy. Like on the surface, you would think, wow, this is great. I got a free puppy. Puppies are expensive, $500, $600, $1,000, $5,000. But your cost doesn't stop there. Your cost will increase from that point. The maintenance cost, the shots that you'll have to give that puppy. So, yeah, there are a lot of real-time kernels that are available for free, but just think about it as a free puppy.
And for those of you wondering, perhaps you've heard me use the free puppy analogy. I believe I stole it from Jean many years ago.
Okay, I know I'd heard you say that.
You've definitely heard me say free as in puppy. Yes,
having a big moment of deja vu there.
Yeah.
So you're convinced then? That's good.
Well, and there's always something to be said for when you're making a real product in a real company. There's always something to be said for having an external party to yell at.
Well,
you're paying for support, and so you can go and say, "Help me, this doesn't work."
Yeah, but it's mostly that. It's support. It's peace of mind. It's somebody that you could always fall back to, because invariably, as the applications are getting more and more complicated, you will need help. You're not an expert in RTOSs and protocol stack. You're an expert in your own application, whatever that is. So you don't want to spend your time debugging, or if you have to debug, you want to have somebody to help you with that debug stage that understands the intricacies of multitasking, protocol stacks, file systems, and so on. So you want to concentrate on your application. That's not what you're paying that money for. If you're on your own, and I see that a lot. It means, hey, I'm going to save a lot of money to my boss. I'm going to get some free operating system somewhere. I'm going to save a lot of money, and it turns out that I guess your weekends are not free or not. You got to spend weekends potentially to debug things that you could just call somebody on the support line to help you out with. And it's like anything else. We've seen a lot of these issues that people bottom line, we see pretty much the same issues over and over again. So for you, it's a new issue. For us, it's something that we've seen many times, and we would most likely answer those questions fairly easily, fairly quickly. Whereas you're novice to any use of the software. So it's a lot easier to ask somebody sometimes than it is to dig and spend the whole weekend at it.
Yeah, because you're going to have to, if you take in a free project, you either have to depend on forums and talking to the community, and which will answer you at whatever rate they feel like, or you have to take ownership of it. And okay, you're going to have an internal team that's devoted to finding bugs, and making the changes you need to make. So it's a trade-off, right. But you have to, like you said, it's ownership of a living thing, kind of.
Exactly. And software is a living entity. Software changes. There are things that don't change. For example, the kernel has been extremely stable. We rarely make drastic changes to it. If it's not broken, it's working fine. It's got certifications to it. So we don't want to change the kernel itself. TCP/IP, I mean, of course, there are new protocols we're adding. File system, there's new devices we need to support. So software is really a living entity, new protocols and new things that you want to add, new drivers, new devices. You want to benefit from that. We're in the business of doing that on your behalf so that you could concentrate on your application.
How does the purchase of Micrium by Silicon Labs change things for you or for MicroCOS?
It actually doesn't change anything. The marching order that we have from Silicon Lab is that we will be maintaining our support for all current customers, irrespective of the platform that will be that the customer will be using. So we'll be supporting just about everything. I mean, we made it very clear to Silicon Labs when we were acquired that what we care about is our customers. We want to support them. We don't want to let them. We don't want our customers to hang, and thus, we need to support all these different platforms. And, oddly enough, I mean, Silicon Lab has Cortex-M processors, but they don't support all the different Cortex family. We don't have anything with Cortex-A's. We don't have anything with Cortex-R's. We don't have, of course, PowerPCs and RX and all these other platforms. So all the customers that have used our software in the past, last thing we want to do is, abandon them.
Good. That's a good thing to hear.
Yeah.
One worry I heard was that they were going to maybe not let you put your book for free on your website anymore.
That's not true. Actually, the book is still going to be for free, and we will continue doing that. In fact, we have started this program called the MicroCOS for Maker. We'll maybe rebrand that a little bit differently, probably called it Micrium for Makers. But the idea is that you could use any of our software in source form if you're a maker, a hobbyist, a student, a professor. So you could use all of our software, OS, TCP/IP, file system, USB host, USB device, Modbus, anything that Micrium or in this case Silicon Lab owns the IP to from the Micrium acquisition, then we will still offer that for free use. And it's not the crippled version; it's the exact same version that commercial entities. So the concept there is just like when I came up with the MicroCOS 1, 2, and 3 books, is we provide the source code of the software for people to use. And as you could imagine, it's an honor system, so we can't really control because we're opening that up in source form. What we want to do is we want to get people to use clean commercial grade software to play with. And then the hope is that like professional engineers that work for companies, they play with our software at night or on weekends, come back to work and say, "Hey, boss, I tried the Micrium software. It's awesome, and I would like to use that in our next product that we're doing commercially." And of course, at that point, we're expecting them to contact us to license our software.
And if somebody has been doing bare metal development, like Arduino 8-bit sort of development, and they want to try this, do you have a board or project or path that you would recommend?
Yeah, it's very good question. There's quite a lot of content on our website. In fact, I would say, if anything, you could go to our website. There's a download center. You could download not only the software in source form, but you could also get a whole bunch of projects. We probably have 500 or 600 projects on different eval boards and stuff. So it's very easy to try the software.
How are you going to continue that in the future?
Well, if I could find some hours in a day, it would certainly be nice. But I mean, certainly one of the things that Silicon Labs wants to do is to have me be more, be doing more writing, more presentations, lectures at conferences, write books, potentially do more videos. So that's something that that will continue if I could just kind of like start figuring out how do I delegate all these new assignments that I now have. But eventually, that's the idea. So I really enjoy doing that. I mean, oddly enough, I mean, writing is difficult for me. My vocabulary is very limited. I'm originally from Canada, and my native language is French, but I've been in the U.S. for 30 years, so I don't really have an excuse not to be good at writing and stuff. But it is still difficult, and I guess it's an advantage for me to have limited vocabulary because I don't try to use complicated words to explain concepts. I really try to get to the fact, and I really believe in graphics. I really believe in pictures. I like to explain things with illustrations, graphics, or that type of information. So if you were to look at my book, I think you've glanced over it, you'll see there's a lot of illustrations, and I narrate the illustration in the text so that you could actually follow along the whole process of stuff. So I really would like to continue that whole thing, and I may have a couple books that will eventually, if I could find the time, write about.
I do want to point out to listeners that not only are the books free, I think with registration on the site, there is a book about the Kinetis system and medical that I particularly looked at. And not only was like the first chapter, the really good explanation of real-time operating systems and how they work, the fifth chapter was an excellent tutorial on how to get started into medical. It listed all of the acronyms and all of the papers and all of the government documents you need to look at. It was really quite useful. So everybody who's thinking about writing to us and saying, how do I get into medical? My new plan is to point you to that chapter.
Absolutely. And I don't know which one that you actually got. Did you get the MicroCOS 2 book for with Kinetis, or the MicroCOS 3 book for Kinetis? Because there's two versions of it. Okay, so there's a MicroCOS 3 book. It's even larger, so it will guarantee to put you to sleep at night. So what it is the first part of the book is about 600 pages that explains the internals of MicroCOS 3 in great details, and and each chapter is organized like what is the, for example, what is a semaphore, how to use semaphores, and how does semaphore work. And the next chapter is what is a message queue and how to use message queues and how do they work. So all that is all explained in there. But in that second portion, so that's out of 925 pages, I think 600 is dedicated to real-time operating system and specifically to MicroCOS 3. And then the remaining 300 plus pages really goes into details about the medical aspects of the certification and things like that. But also there's 4 chapters. One is blood glucose meters, pulse oximetry, blood pressure monitoring, and I can't remember what the fourth one was, but very, very cool. So we actually explain the physiology of things, and then we get into an example of how do you implement that using a kernel and using a Kinetis part. And we're using a K53 tower from Freescale, which now was bought by NXP, which is now bought by Qualcomm. I looked mostly at the oximeter one, and I liked all the pictures of like how hearts work, and it got down into the pretty good, interesting biology, mechanical biology, and how light goes through it was very cool. I was happy. Thank you. Yep.
So you're clearly still excited about what you do. And I talk to a lot of people who are getting burnt out or are already burnt out. How do you stay excited about this?
Well, there's so many things, happening. So many, the technology is growing at frantic rates. I mean, the IoT, electric vehicles, the connected home. There's so many things happening, and I read trade magazines and I see, wow, this is new technology. I mean, for example, I was reading the IEEE magazine the other day, and this guy is coming up with a camera that's about the size of a cell phone that's gonna be as good as a DSLR, and in fact, he's trying to get up to like a 600 millimeter lens equivalent. but it's the size of a cell phone. It's flat like a cell phone. It's got like something in the order of 15 or so different lenses of different focal lengths and stuff. So, like, wow, there's still some new stuff coming out. There's a lot of new stuff coming out.
We live in an exciting time.
Absolutely. I mean, like I said, I mean, the cell phone is a computer. It's phenomenal. When I travel, I spend most of my time looking at my phone. I only open up the laptop when I need to do something, very complicated, very, very focused that I can't do on the phone. But the phone, I answer my email, I look at websites, I book my flights, I input my expense. I mean, there's so many things you could do with these things. It's just unbelievable.
Well, I think that's a pretty good note to start winding it down on. Chris, do you have any final questions?
Yeah, sort of following up on new technology. Operating systems have been very similar for a long time in terms of fundamental structure. Is there anything new happening? Are there new concepts, or are we this is how an operating system is going to work for the next couple of decades?
Well, I think the things that's going to be going towards is protection of IP. So, for example, ARM introduced their ARM Cortex-M V8 with trust zone, which basically means that you will be able to hide intellectual property or prevent people from hacking your code or tampering with your software, because it's all going to be built in. They have mechanisms to protect execution of code that's not going to be visible to an application. So you could write an application, so your own application, and purchase IP that you want to be protected, so that either you don't want to be able to tamper with, or you want to protect the IP because you put some value on it. So that ARM V8 architecture, so there'll need to be some adjustments made to the real-time kernel, real-time operating system. But I think it's going in that direction. Security is going to be a huge thing.
Yeah. And I hear a lot about hypervisors too.
Right. Higher end systems sharing the CPU amongst different virtual environments. That would be for very higher end CPUs. I'm not sure we're gonna see that at the Cortex-M type class level, and I still think we'll see. We'll see 8-bit processors, and we'll see 16 and 32-bit processors for a long time without all this memory management units and hypervisors. So, case in point, Silicon Lab has 8051 processors, so and they're quite popular. There's a lot of applications that an 8051 is way plenty.
And in the meantime, we'll keep calling them watchdogs.
Well, not quite. I mean, they have
they
do some fairly complicated applications.
Oh, I meant the hypervisors being watchdogs.
Oh, yeah.
Okay. Well, we have kept you, I think, for long enough today, although I have so many other questions. Do you have any last thoughts you'd like to leave us with?
Well, the one thing I'd like to say is, if you're interested in RTOS, I would urge you to download copies of my book, of course, from our website. They're all free in PDF format. You could go to www.micrium.com. We have plenty of sample code, example in source form. You could actually play with it. We support a large number of evaluation boards, so anything that you fancy, we pretty much support. Also, considering the cost of your time, it should be used to add value to their product instead of writing infrastructure code like RTOSs and protocol stack. And the other thing is, I had mentioned that earlier also, I'd like to urge you to look at or download a copy of our uCProbe product, which is really cool because it works with just about any processor architecture, and it allows you to see at runtime inside your embedded system, and you're able to look at variables, any variable that you have in your your application. And in fact, you could look at I/O ports and display those using gauges, meters, numeric indicators, all kinds of neat stuff. So just check out our uCProbe product on the website. You'll find it quite interesting. You won't need to do printf statements or blink lights or turn on output ports and stuff. And if anything, there's one feature that we've added in there. It's an oscilloscope, so you're able to tap in and look at any variable in your application and throw that on an oscilloscope tray. So very useful for monitoring or looking at real-time applications. So that's it. Thank you for your time.
Those links, of course, will be in the show notes. And thank you, Jean, for being with us. Our guest has been Jean Labrosse, author of MicroCOS, the real-time kernel 1, 2, and 3, founder of Micrium and chief architect at Silicon Labs. His books are on the micrium.com site. In case you're wondering how to spell that, that's MICRIUM.com. Link in the show notes, of course. Thank you also to Christopher for producing and for co-hosting. And of course, thank you for listening. For those of you waiting for stickers, you're just going to have to wait a little bit longer because, wow, you all wanted stickers this time, and I'm happy but slow. If you want stickers or if you just want to say hello, hit the contact link on embedded.fm. You can also sign up for the newsletter, subscribe to the YouTube channel on Embed.fm, or you can read the blog, which is pretty darn cool. Okay, and now a final thought for you from Jean de La Fontaine from Fables. A person often meets his destiny on the road he took to avoid it. Embedded FM is an independently produced radio show that focuses on the many aspects of engineering. It is a production of Logical Elegance, an embedded software consulting company in California. If there are advertisements in the show, we did not put them there and do not receive any revenue from them. At this time, our sole sponsor remains Logical Elegance.